Hi, my name is Madison Maxey, and I'm the founder and CEO of Loomia. Today, my goal is to tell you a little bit about electronic textiles and then walk you through a case study of where e-textiles came in handy for an application in robotics. All right, here we go. So I like to start off with a little bit about what exactly are e-textiles, or what will be the definition that I'm using for e-textiles today. And I always like to bring up this example of the difference between conductive thread and an e-textile system. So in our eyes, something like a conductive thread is just a conductive material. It's not an electronic textile because it's not a system. For us, electronic textiles are materials like these, where it's the same thing as a circuit. You have a load, you have a power source, and you have pattern traces in order to conduct electricity in a way that you desire. So whenever I talk about e-textiles, I'll be talking about these systems today. In our view, electronic textiles, which are also known as soft circuits, are a foundational technology, an ingredient, if you will, that allows us to merge soft goods and electronic function. And in some cases, they're great for hard electromechanical problems. So why are they useful? Well, we're in touch with textiles for 97% of our lives. So they're everywhere from automotive interiors to bedding to industrial workwear. And electronic textiles can add functionality to those textile surfaces. Depending on the application, they can do things like lightweighting, improved design, robustness, cost savings, and manufacturability for certain kinds of applications that you might be working on. So for this particular case study that I'll work you through, we have a goal of improved robustness or better durability in switching from a flux PCB to an electronic textile. So the Loomia electronic layer, which I'll mention throughout this presentation, is our own patented version of an electronic textile. We have a soft, flexible circuit system that we developed that laminates to textile A-class surfaces in order to add functionality to those materials. And our technology is just a part of the whole system. So the circuit that we create actually isn't very textile when you look at it. It's a laminate, and it gets laminated to a fabric, which is where the e-textile system happens. So what can these materials do? Our e-textiles can do things like heating, pressure sensors, or sensing pressure, cabling, and user interfaces, as well as lighting, which you'll see in the example that I have later in this presentation. All right, so getting to our case study, I just wanted to walk you through the process of designing and engineering a custom electronic textile application using our technology. And my goal is to sort of paint out the pain point and the solution throughout this presentation. So we talked previously about why e-textiles are useful. And for this particular project that we were brought into with Festo, which is a robotics company, they were interested in getting better robustness for sensors on the digits of one of their bionic hands. And so when you're using a flux PCB, it's only meant to have unidirectional flux in most cases. It's not meant to really move back and forth and up and down, kind of like the finger on a hand would. So by switching to electronic textiles, we were able to give the kind of drapability and multi-axis flux that you get from a textile for this robotic hand. And the process for developing something like this happens in a program that we call the Loomia Lab. And the Loomia Lab has two phases. The first one is research and development, and the second one is fabrication. The R&D phase is where we're sourcing different materials, we're testing things, we're really in touch with the customer and iterating. And the second phase is fabrication. That's where we're actually making the proof of concept and handing over a functional prototype that they can then test and validate with. So the actual functional prototype from this project, I'll show you as we walk through this process. Some of the features of the pressure sensitive matrix and glove that we developed for Festo are that this glove has a 113-point pressure matrix. We did the design and production. It also has a backlit logo just for decorative features, and it has a fully integrated PCB